Okay, this is my video report for Lab 5, Magnetic Braking with Faraday. A quick overview of this video report: I'll introduce the experiment and relative physics principles, the calculations and code for the experiment, and then conclude with further questions. So the goal of this lab was to deepen our understanding of Faraday's law by collecting data of a magnet falling through a cylinder made of conductor material, specifically aluminum foil, and then the current induced by the magnet as it falls through the cylinder. How the experiment worked is I rolled a sheet of aluminum foil to make a tube, took necessary measurements of that tube, which I'll discuss later, and then dropped a magnet through the foil 5 times so I could average the time taken for the magnet to fall through it. It fell much slower than it did through free space, which was pretty cool to watch, and also indicates that there were different forces acting on it than just gravity, specifically magnetic force. I then did the necessary calculations to get a theoretical value for the time taken to fall through and compared the experimentals to the theoretical value, so they were surprisingly very similar. My final results are here, which builds a strong case for taking multiple trials worth of data. But importantly, the presence of a magnetic field from the cylinder indicates that the magnet induced a current in it, which created a magnetic force which opposed its gravitational force and caused it to fall slower than it would have through free space. So some important underlying physics principles, like the ones I just discussed. We have Faraday's law for the induced current in each of the rings as the magnet falls through it. That's the derivative of flux with respect to time, gives you the EMF value that's generated. We also need the Biot-Savart law so we can calculate the force generated by the magnet on each ring. And then we need Newton's laws so we can calculate the force of gravity acting on the magnet, and also so that we can equate the equal and opposite forces of gravitational force and magnetic force from the cylinder. We also have resistivity, which comes from the aluminum foil and is based on its material properties. So then this is my experimental data. The values measured for the aluminum foil cylinder are on the left, and then the magnet data comes from my results from Lab 3. On the right are the times I recorded, and the average came out to be 1.274 seconds, so sig-fig-wise 1.27 seconds. We have to expect this value to be prone to error due to a human error on my part, like with the stopwatch, for example, or not holding up the tube perfectly straight, or with an underlying assumption we made for the model that may not be perfectly true in the physical world. So we have to anticipate some error there or uncertainty. And then I perform my calculations for the theoretical time in glow script. The code is pictured on these next slides. These are the images for initializing the values, and also where I inputted the measures values relating to the magnet and the aluminum foil tube. Then we have the code to model 2 necessary functions. So we find the magnetic field generated by the bar magnet. So we treat that as a dipole. And then we also have the magnetic flux passing through a ring generated by the bar magnet. We treat that as a series of rings to generalize the geometry of the cylinder. Then there's the code to actually create the simulation. It's a bit long, so you can pause it to read it more carefully. The simulation shows a magnet dropping through a tube for a time t and generates a velocity versus time graph when it runs. Seen on the next slide here, we can see the calculated time for the magnet to fall through based on the magnetic force and the magnetic field generated by the aluminum foil opposes the force of gravity. And in a perfect simulation, it would be 1.27 seconds, which is amazingly very close to my experimental value. Even with the very close similarity, it's important to consider assumptions we made about the experimental and theoretical models. So in the physical experiment, I assumed that the tube was held up perfectly straight and the magnet fell through it perfectly straight, so it stayed equidistant from the sides at all times. the very center. And then, because if there's any variation in that, it's going to be interacting with a magnetic field differently, because the forces in the x direction and y direction are not going to be the same. And then for the calculated time, we assume that approximating the magnetic field to be a series of rings stacked on top of each other is an appropriate model for the B field. Discrepancies between these assumptions and real-world phenomena would cause differences between the values and what they're actually supposed to be. And now for some extension questions to conclude. If the resistivity of the aluminum foil was reduced a lot, what would happen? Well, the resistance would also decrease, since resistance equal resistivity times the length of the material divided by a cross-sectional area. Since resistance is in the numerator there, resistivity is in the numerator there, resistance would also decrease. And then if resistance is lowered, then in order to balance out your EMF value, the induced current has to increase to compensate. And then with a larger induced current, the magnet would fall through the foil much, much slower. On the other hand, because your magnetic force is increased. Then on the other hand, if we were to cut holes and slots in the foil, we would be taking away material, which helps to generate a magnetic field, so you would have fewer rings in the model. And then with fewer rings, the magnetic field generated by the foil decreases, and thus the induced current also decreases, so the magnet would fall through much faster.